So the next talk is going to be by Tushar Mopuri from the University of Pennsylvania on a new framework for constructing hash-based proof systems with efficient prover time and query complexity.
Thank you.
So, yeah,
Thanks.
feel free to start.
Thank you. Yeah. Hi, everyone. My name is Tushar, and today I'll be telling you about a new framework for constructing hash-based snarks. Yeah, I'm just waiting, I guess, for the slides to come up. Maybe something to explain while we wait is, so this work is based on two papers that are accepted at Eurocrypt and more recently Crypto. But weirdly, the paper that we wrote first got accepted second. So I'm using a more like intuitively correct citation here, which is BMMS 25 for the first paper and 26 for the second paper. Although technically the second paper is 26A at Eurocrypt and the first paper is 26B at Crypto. So just letting you know. But yes, so right now it's intuitive. 25 is the first paper, 26 is the second paper. And this is joint work with Anubhav, Pratyush, my advisor, and Matan. Okay, so let's get started. All right, so the first thing I should tell you I don't think this is working. Yeah, I mean, it's partly my fault, I think. Yeah. So, what is the problem exactly? Maybe I can help. Okay. It was a keynote file. It was a keynote file, and yeah. So can you just flip through this and see if there are even slides there? Maybe they just didn't compile it correctly. Yeah, I don't think this is the right file. Yeah.
So I opened it. This is the file it shows me inside the zip.
Okay, so I have my laptop. Do you think can I connect mine? Yeah.
Yeah.
Yeah. Can you hear me? Okay. Yeah. So I'm going to tell you how to build hash-based proof systems in a modular way. But before I do that, I should probably remind you. This isn't working. So one thing I can do is I can make a PDF and I can send it. I can email it to that laptop. Should I do that? It'll take 2 minutes.
To make a PDF.
Yeah, I'll send it to you.
Wait, I have another clicker. Maybe that's easier.
Okay. Do you have a clicker? Oh, that would be awesome. A Mac. Yeah, I don't know. I guess maybe they didn't see anything. Oh, we already have one. It's just not working. Thank you. Should I? Do you have an email ID I can send a PDF to? Okay. Honestly, I just have I've a PDF, so I'm just going to.
Okay.
Yeah, I can.
You know which email?
I'm putting it in the pen drive. I'm putting it in the USB. So it's over there. Yeah, I'm gonna need the thing. Grazie. Yeah, okay. So let's start by motivating why we even care about hash-based snarks. So why do we need snarks? Snarks are the most important, if not one of the most important primitives we study in proof system design. And in particular, a goal is to build snarks for all computations in NP. And a very fruitful recipe for doing this has been hash-based snarks, where you build this thing called an interactive oracle proof for NP, and you apply the BCS transform to it, which uses just hash functions, which is why they're called hash-based snarks, to obtain a hash-based snark for NP. At a high level, how an IOP, how all modern IOPs at least work, is a prover tries to convince a verifier that it knows a satisfying witness such that a shared instance X is in the language. It does so as follows. It takes its witness, encodes it under an error correcting code C, sends a oracle containing this encoded witness to the verifier, and the prover and verifier run what is called an IOPP, an IOP of proximity, where the prover convinces the verifier that this oracle contains something that is close to a code word of C. And the verifier, by querying just a few points in this oracle, accepts or rejects this claim, and we need this to satisfy the standard properties of completeness and soundness. So the efficiency of hash-based snarks is determined by, one, the encoding time of C, because the prover has to encode the witness, and two, the efficiency of the IOPP for C. That is prover time, verifier time, query complexity, and so on. So In this talk, we're going to focus on building efficient IOPPs for efficient codes, that is, linear time encodable codes. Let's look at what kind of prior IOPPs we already have, and I'm going to focus on IOPPs with negligible soundness error because that's what we want in practice. A seminal result is Fry, which built IOPPs for the Reed-Solomon code with linear prover time and lambda log n query complexity. Another breakthrough result, Stir and Whir, brought the query complexity down to lambda log n. And the recent work, Minzer and Zheng, builds IOPPs for trivariate Reed-Muller codes with order of lambda query complexity. The issue with all of this work is that the codes are quasi-linear time encodable. And this means the prover time is sort of bottlenecked by this. So there's been another line of work that considers IOPPs for linear time encodable codes. In particular, the first one is BCG20, which inspired also the more popular breakdown IOPP. And these are IOPPs for interleaved or tensor codes that are linear time encodable that have sublinear query complexity, lambda n raised to 1 over t for any constant t. But it's not quite logarithmic, the query complexity. Simultaneously, Blaze and Breaking Base brought the query complexity down to lambda log n for linear time encodable codes, in particular the repeat accumulate code and breakdowns expander code. There's also another line of work that considers linear prover time, but constant soundness error. This is more theoretical work, and it has been very influential in terms of techniques, but I won't go into the details for this talk. So now the question is, can we get the best of both worlds? Can we build order lambda query, like state-of-the-art order lambda query complexity IOPPs for linear time encodable codes? In our work, we answer this question affirmatively. We build IOPPs for linear time encodable codes with the desired efficiency. And in particular, we handle a large class of linear time encodable codes, which are called code switchable codes. This includes all tensor codes, so any tensored linear time encodable code will do, or more practically relevant are LDPC codes, which include both codes I mentioned on the earlier slide, breakdowns code and RAA codes. I should mention that a concurrent work doesn't syntactically build IOPPs, but they build a primitive that implies IOPs with the same efficiency. Okay, so how do we do this? In our first paper, we build a modular framework for constructing IOPs. This modular framework uses these things called interactive oracle reductions, which I'll talk about shortly. But we systematically study IORs and their composition, and we present a new security definition for IORs. We also study the compilation of IORs to non-interactive arguments and reductions. And we give a theorem for this in the ROM, the random oracle model. We also present new IORs for code switching, which I'll get into later in the talk, and these turn out to be quite interesting and useful. So the overall goal for this talk is going to be to prove lemma 1, which we proved in the second paper, which is, well, I'm going to prove theorem 1, but to complement theorem 1, we also show in the second paper lemma 1, which says that this state-of-the-art order lambda query complexity is also optimal. You cannot hope to have IOPPs for constant rate codes with, lesser queries than this. And constant rate implies constant distance. And essentially why this constant rate codes is relevant here is that all linear time encodable codes must have constant rate. If you had worse than constant rate, then you cannot encode in linear time. Okay, so let me give you what to expect in this talk, a high-level roadmap. First, we're going to talk about what IORs are. Then I will give you a formal definition of IOPPs. And then I will give you a warm-up IOPP construction, which is essentially the construction in our first paper with lambda log n query complexity. Lambda log n query complexity in this talk. And then I will give you our final construction from the second paper. So what is an IOR? An IOR deals with oracle relations, which are an extension of NP relations, where there's not only an instance and a witness, but there's also an instance oracle Y, where in the context of a prover and a verifier, Y is part of the instance that is very large, and the prover has full explicit access to Y, and the verifier only has oracle access to y. This is essentially going to be the oracle that we're running the IOPP for. So an IOR from an oracle relation R to an oracle relation R prime essentially reduces the task of checking membership of X, Y, W in R to checking membership of a related instance in R prime. How you do this is the prover sends oracle, the prover and verifier interact, where the prover sends oracles to the verifier. The verifier replies with like public coin randomness, random challenges. And at the end of the interaction, the verifier queries both the instance oracle Y and all the oracles received in the interaction, and outputs X prime and chooses a Y prime by concatenating oracles received through this interaction. So Y prime is formed by concatenating Y, possibly any subset of Y and these oracles received during the interaction. And the prover outputs a new witness W prime. And as long as X prime, Y prime, W prime are in R prime, the verifier is convinced that the original X, Y, W are in R. Or more formally, completeness says if X, Y, W is in R, then this output must be in R prime. Soundness says that if the output wasn't in R prime, essentially, then regardless of what the prover did, it couldn't have been the case that the original thing was in, then regardless of what the prover did, you're convinced that the original thing wasn't in R. Or sorry, actually, maybe I should say it like, if the original thing wasn't in R, regardless of what the prover does, it cannot make it so that the output is in R prime. And the neat thing about IORs is they behave well under composition. That is, if I had an IOR from R to R prime, and an IOR from R prime to R prime prime, I could run them in sequence to get an IOR from R to R prime prime. So IORs are a generalization of IOPs, and you can recover the traditional definition of an IOP by setting the output R prime to be a trivial relation. So instead of outputting some non-trivial output, the verifier just accepts or rejects. Okay. Another preliminary we'll need is multilinear polynomials. I'm sure you're all quite familiar, but let's do a quick run through. Multilinear polynomials are mu-variate polynomials of degree at most 1 in each variable. And they can be represented either by their coefficients or by their evaluation over the Boolean hypercube. And we use m hat of x to denote the unique multilinear extension of a vector m. So m hat is essentially the interpolation of m. That is, m hat evaluates over the Boolean hypercube to m. And the seminal sum check protocol is the backbone of many modern IOPs, and it reduces the task of proving a claim about the sums of evaluations of a multivariate polynomial to a single evaluation of the multivariate polynomial. Okay, so now we're ready to define IOPPs. In this language that I just defined, an IOPP is an IOP for this oracle relation, where the instance oracle contains a vector W, and the prover claims that the distance of W from a code word in C is at most epsilon. And in particular, this code word is the encoding of the witness message M. So for the rest of this talk, I'm going to use this more intuitive notation for saying W is at most Hamming distance epsilon from the encoding of M. And I glossed over an important detail earlier, which is while IOPPs of this form suffice for Reed-Solomon codes, for arbitrary codes, in particular linear time encodable codes, it doesn't suffice just to guarantee that W is close to the code. You also need to prove an evaluation claim about the underlying message M. In particular, we add to the instance, the short instance, a Z and a Y, and we say that not only is W close to the encoding of M, but also M hat of Z equals Y. This is essentially a polynomial commitment scheme. You commit to the message M, Y or W, and then you have an evaluation claim over M hat. We also define a more expressive relation called SEP, which has a proximity claim. It's called so MEP stands for multilinear evaluation and proximity, and SEP stands for sum check evaluation and proximity. So for the sum check claim, on top of the proximity claim, we have a claim of this form, which might look really intimidating, but all it's saying is that the inner product of M and V is sigma. So v is a public vector we put in the instance, and sigma is a claimed answer. And the reason we do this is because we can set up very expressive claims of this form. I can commit to a message M by encoding it, handing you the encoding, and I can promise you that the inner product of M with a large V is sigma, and we can reduce this via an IOR called sumcheck, a sumcheck-based IOR, from SEP to MEP to an MEP claim. How you do this is you take the SEP claim, you run sumcheck to reduce it to evaluations at a random point, you move things around, and you have now an evaluation claim over the message, as opposed to a sumcheck claim. Okay, so let's see how to use this to relatively easily build a already non-trivial IOPP. In the first paper, we build an IOP for MEPC, which is an IOPP, with order lambda log n query complexity. We do so for a C that comes from a family of codes of varying message lengths. In particular, let's think of our starting C as CK, the code from the code family with message length k and block length order of k, that is constant rate. How we build an IOPP for CK is by defining S to be log k, and we will build a sequence of reductions. I'll tell you how these reductions are constructed shortly, but we'll build a reduction reduce 1 from CK, MEP CK to MEP CK over 2, and then reduce 2 from MEP CK over 2 to MEP CK over 4, and so on. So each of these reductions is basically reducing checking proximity to a code of length k, of message length k, to a code of half that message length. We are reducing essentially the witness length by half each time, and towards the end, the message length is so small that you can just send the witness in the clear. Each of these reductions has linear prover time and order lambda query complexity. How do we put this together? Again, so you start off with this claim with respect to CK, right? I'm telling you that W naught is close to CK, and the underlying message satisfies an evaluation claim. Maybe it'll be simpler. Actually, yeah. So then you run this sequence of reductions, reduce 1 up to reduce S, and you output claims with respect to C1, whose message length is just 1. And the block length here in this figure for WS is 2. So message length 1, block length 2. All the verifier needs to do to verify the final output is to query the entire word. The prover sends the tiny message in the clear, and the verifier can directly check this MEP C1 claim. Completeness and soundness follows from our composition theorem of IORs, as long as each of these IORs are complete and sound, which I will explain shortly. Overall query complexity is adding lambda to itself log n times. And the overall prover time is a geometric sum, so it's also order of n. Okay, so let's construct these reductions. We're going to construct a linear time IOR reduce from MEP-CK to MEP-CK over 2 with order lambda query complexity. As I said, essentially what we're doing here intuitively is reducing the message length in half. And how we do this at a high level is by folding the message in half. Now the issue is CK itself might not be especially amenable to such a folding. So what we're going to do is first reduce checking proximity to CK to reducing proximity to some C prime that's more amenable to folding. And then we're going to fold from C prime to CK over 2. So the first task is accomplished by code switching, a code switch IOR. This is a very fruitful notion that was introduced in a theoretical line of work, but has since bled into practice, where essentially you reduce checking proximity to one code to reducing checking proximity to another code. And in our first paper, we present an IOR that lets you reduce checking proximity to a tensor code to checking proximity to an arbitrary C prime, right? And we also formalize another existing IOR that reduces checking proximity to LDPC codes to arbitrary C primes. So between these two things, you can handle a CK that's any tensor or LDPC code, and you can code switch to an arbitrary C prime. This is why we can handle all tensor codes and LDPC codes. And now we're left to tell you what the choice of C prime is. We choose C prime to be the interleaved code obtained by interleaving CK over 2 with itself twice. What this is essentially you take a message M of length K, you split it into two halves, the left and the right half, and you encode each half under CK over 2. This is the interleaved CK over 2 code. So we use the existing code switch reduction to reduce checking proximity to CK to checking proximity to ICK over 2. And now I'm going to tell you how to fold the ICK over 2 claim into a CK over 2 claim, right? And you do this sort of as you might imagine. You take this claim with respect to the interleaved code. For the rest of the talk, actually, I'm going to drop the evaluation claims because they're typically easy to like add on top of things, and the proximity claims are really the hard stuff. So let's focus maybe only on the proximity claims. So we have this proximity claim with respect to the interleaved code, and we want to reduce it to a proximity claim with respect to just CK over 2. How you do this is by having the verifier sample a random challenge gamma, and the prover sends over a claimed CK over 2 code word, which is supposedly the encoding of, which is supposedly the linear combination essentially of WL and WR, the two halves of the interleaved code with respect to gamma. The verifier performs now new spot checks, which involves sampling new equals order of lambda many random indices in these code words, right? And for each I in new, the verifier queries WL to obtain LI, WR to obtain RI, and W prime to obtain sigma I, and checks that at these spots the claimed relation holds. That is, that W prime equals WL plus gamma times WR. If all of these spot checks pass, then the verifier accepts that as long as W prime is close to CK over 2, the original thing was close to the interleaved code word. Why is this sound? Let's say the initial thing was not close to the interleaved code word. What that must mean is either the WL is far from the code, either WL is far from CK over 2, or WR is far from CK over 2. And so proximity gaps, which are a very well-studied notion, says that if you linearly combine two code words, if either one is far from the code, the combination is also far from the code. So this tells us then that the linear combination must be far from CK over 2. And the spot checks enforce that W prime is not far from the linear combination. This is because if W prime was very far away from the linear combination, and we checked at new many points that W prime agrees with WL plus gamma times WR, we should have found some point where these things disagree. So between knowing that, so essentially, either one of the rows must be far from the code if the original thing wasn't in the relation. That means the linear combination is far from the code. And since W prime is not far from the linear combination, it must also be far from the code. Any questions at this point? Okay. Cool. So we have the warm-up IOPP, which is obtained by then applying this reduction log k many times. Now the issue is this only has lambda log n query complexity, and we were aiming to construct a reduction with order lambda query complexity. So how do we build query optimal IOPPs? What do we need? So the issue so far has been that we have log k many reductions with order lambda queries each. What we need is constantly many reductions with order lambda queries each. Now, you might hope alternatively to bring the number of queries themselves down, but there are some lower bounds that say you can't do this. So if we are stuck with reductions that have lambda queries each, we must reduce then the message length by more than a factor of half each time. The good news is it suffices to reduce the message length to order k to the 1 over 3, as opposed to all the way down to a constant as we did earlier. Why does it suffice to only reduce the message length by a polynomial factor? This is because at this point, you can use our generic code switch to code switch to a Reed-Solomon code with inverse polynomial rate. So this is a Reed-Solomon code with a lot of redundancy, like a very large rate. And then you can use existing IOPPs, in particular were, which we typically think of as having lambda log n query complexity. But if you start with a really large rate, were actually already gives you order lambda query complexity. So it suffices to reduce the message length only to k to the 1/3, and then use a word IOPP for codes with very large rate. So our goal is just to build a reduction that reduces then your message length from k to k to the 2/3, and apply this a couple of times to reduce the overall message length to k to the 1/3. Okay, so how do we build a reduction that shaves off a polynomial factor from the message length? Naive idea could be to interleave more, right? So we've been using a interleaving factor of 2. What if instead we interleaved k to the 1/3 many times, right? So we code switch out from the initial ck to something with an interleaving factor of k to the 1/3. And we used sort of the existing idea. We still perform new many spot checks and the verifier checks that essentially when you fold down this thing, you obtain the output. The problem is that when your verifier performs these checks, it queries entire columns of this interleaved code word. And as described, this requires lambda times k to the 1/3 queries, which is too many. So what do? So I'm going to make an observation, and I'm going to see maybe if any of you can guess what we do at this point. The observation is that the check performed by the verifier in a spot check is essentially a check of the following form. So initially, we would query ML and MR, and we would check that the first thing plus gamma times the second thing is equal to something. That is, we're checking a inner product claim with respect to the queried column. So when you generalize this to the k to the 1/3 interleaving factor, you essentially query column CI and check that the inner product of CI with some public VI is equal to the sigma I you queried down there. So we have this problem with the query complexity of not wanting to query entire columns. But we know that the guarantee we want from the column is just an inner product claim. So what do you think we might do at this point? Exactly. So yeah, we have this SEP relation that gives you exactly this promise, that some committed message satisfies an inner product claim. The issue is that these columns, however, are not committed to. They're not encoded. They're just in the clear. So what we can do is encode the columns. So instead of code switching out to an interleaved code, we code switch out to a tensor code, where you encode each of the rows, and then you encode all of the columns. And now, for each spot check, instead of the verifier performing this inner product check itself, the prover will convince the verifier that this inner product holds for the underlying CI. Okay, are we done? Unfortunately not, because if the verifier was to check each of these new SEP claims on its own, even if we had and we don't even have this yet, but let's say we had an optimal way to check SEP claims. There is a lower bound that says you cannot check an SEP claim with fewer than lambda queries. So each of these things will have to be checked with lambda queries, which leads to a total query complexity of order of lambda squared. So we're not quite done yet. We've brought it down. We've managed to bring the message length down from k to k to the 2/3. We've shaved off a polynomial factor with order lambda squared queries, but we need to sort of go a little further. And how we go further is we have the prover help out even more. So we have the prover instead define this m prime prime, which is, it promises you that m prime prime is the concatenation of C1 up to C new. That is the underlying messages for the columns you've queried. But you don't know this yet, so let's denote this by C star, right? So the prover concatenates all the columns that you would want to perform these inner product claims with. it encodes this, it commits to this essentially, and sends you the encoding W prime prime. And now using an SEP claim over W prime prime, you can certainly guarantee that for each I, C star I inner product with VI is equal to sigma I. But something you don't know is that these C stars are precisely the CIs under this initial code. We need to check consistency between the C stars underlying M prime prime and the CIs underlying this tensor code word. And as things stand, how you might do this is you would use these existing, essentially you would adapt the code switching techniques to do this. But the issue is essentially summarized as follows. So you want to check that this M prime, let's just focus in on C star 1, right? So underlying this W prime prime, there is a C star 1, and you want to check that it's the same C star 1 as the C1 here. You would do that by querying this tensor column code word. But this column code word has constant distance. So to perform this query, to perform this consistency check with negligible soundness error, you have to make lambda queries to this, which, as we saw, is too many queries. So we would like to somehow only make a constant number of queries per tensor code word column. To do this, we essentially relax the guarantee that the prover is giving the verifier. Instead of telling the verifier that for all new queried columns, an inner product claim holds, the spot check holds, what we're going to do is we're going to increase the number of spot checks from new to 4 new. We're going to blow up the factor. But now instead of telling you that for every single point you queried, the inner product holds, the prover is going to give you a weaker promise. It's going to say, go ahead and sample 4 new columns, right? I'm not going to convince you that every single column folds correctly, but I'm going to convince you that 3/4 of them, some 3/4 of them fold correctly. So the intuition here, I will sort of give you a more formal argument for why this suffices. So this is a weaker guarantee, right? Initially, we used to sample lambda points, and the hope was that if you guarantee that every single one of the lambda holds, I must have caught you at some bad column. Now I'm sort of giving you a choice, like a little more freedom. You can pick which 3/4 fraction you're going to convince me something of, essentially. The intuition for why this holds still at a high level is that you're still getting a guarantee about some 3 lambda many columns. So you still have a good chance of catching the prover. And more formally, we use a Chernoff bound to show that this weaker guarantee suffices. But let's say you believe me that if a prover convinces me of this weaker guarantee, I would be happy, right? Having weakened the guarantee, I still have to convince you that this guarantee is, so this guarantee is not too weak, but is it weak enough? Can we now, only perform a constant number of spot checks per column? The answer is yes, right? So essentially what we do now is we query, so now there's 4 new many things underlying this M prime prime, and for each one we perform a constant number of like consistency checks with respect to this. And why this remains sound is as follows. Right, so we only perform a constant number of queries per column. And just to remind ourselves of what we've done here, we have queried essentially 4 lambda many columns, right? And we're performing a constant number of queries per column, so that's still overall order lambda query complexity. So as long as this is sound, we are done. So why is this sound, right? Let's try and sort of give you an intuitive idea of why this is sound. Let's assume for now that the distance of the code, by the way, is half, just for simplicity. So essentially, half of the columns are bad. Half of the total columns. So what we're assuming is the distance of this code here is half. So if the initial thing was far from the code word, some half of the code words, some half of the columns are bad. So when you sample your 4 new many columns, we should expect that the number of bad columns you sampled is concentrated around 2 new, right? When you sample independently from something with half fraction of bad columns, you expect the number of bad columns in your sample thing to be about the same. Now the prover is promising that there are 3 new good columns in my 4 new, right? So the multiplicative Chernoff bound says not only is the number of bad columns concentrated around 2 new, it's concentrated exponentially so. So the probability essentially that you are bounded away from this expectation by this constant factor is negligible. So essentially the Chernoff bound says that the probability that there are 3 new good columns in the 4 new columns you sampled is negligible. That is, the prover will then have to convince you of a incorrect statement, right? The prover tells you that 3 new of the 4 new things you sampled are good, but there's no way this is true. The Chernoff bound tells us this. So how is the prover now going to convince you of an untrue statement? It's not. This is essentially done as follows. So if there don't exist 3 new good columns, that means at least new of the 4 new sample columns are bad. And it's true that now we've relaxed to perform only a constant number of queries per column. So the prover can cheat in any given column with constant probability, right? Which might sound weak, but the good news is there are new equals order lambda many bad columns. So the probability that you have to cheat in all of them. So the probability that you can cheat in all of them is 1 over 2 times 1 over 2 times 1 over 2 new times. So it's also negligible overall. And so we've constructed the reduction we've set out to construct. And in conclusion, now we have IOPPs for linear time encodable codes, tensor and LDPC codes with optimal prover time and query complexity. Thanks for listening. These are the links to our 2 papers. Thank you.
Yeah, hello. Sorry for the technical issues. Thank you for the very nice talk. We have time for one quick question, and then because there is already a session in place in parallel. Anybody? So, so thank you for your talk.
Yeah.
And yeah, I was just curious about the concrete parameters because I understand that.
Yeah, the concrete parameters are not so good. Essentially, at high level, they come from 2 points. One, we need the row code itself to already be a tensor code also, so that you can code switch out of it at the next level. So essentially, we're tensoring at 2 levels, and each tensoring reduces your distance. So overall, the concrete distance is really bad. So your concrete number of queries is pretty bad. Yeah, so I guess the concrete query complexity is not good.
Okay.
How you solve it is an open question.
All right.
Yeah.
Thank you.
Thank you.
Okay. Thank you. Let's thank the speakers again.